We are working now in the bonding, the third chapter. We are working in that one. Okay, this is the chapter we are working in it. The ionic bonding we already discussed. Ionic radii, polarization of ions, physical properties are already done. Covalent bonding, electronegativity and bond polarity, bonding in discrete simple molecules and dative covalent bond. Almost everything is done, but we'll still go there. Now moving on to the pages, then we'll move on to the shapes of molecules also. Okay, shapes of molecules and ions, non-polar and polar molecules. Then later on the metallic bond, introduction to solid lattices, structure and properties. Okay, and then the exam practice question, we know it from these ones. So at the moment we are going to move on to that particular part. Okay. Now we discussed about bond length, electronegativity and bond polarity. That's what we were discussing yesterday. Okay, and this was the table which we were working on. Quite important table, right? This one. And I told you the electronegativity differences also. Okay, Hazim was waiting, so fine. Okay, the distribution of electron density. There are two types of distribution of electron densities. This is the first distribution which you can see here. It's our topic for today. This is the first distribution in which both the nuclei are exactly at the center, and you can see the distribution is quite equal. Okay, it's an equal distribution, so the two nuclei are exactly at the center. This is called non-polar. There's no polarity. Polarity means unequal distribution of charge. Okay, so it's non-polar actually. And when we're moving towards the second structure, you can see the electron density. This is a polar bond now. For the polar bond, you can see that the electron density, these are the two nuclei, nucleus number 1, nucleus number 2, and the electron density is like this. So it's not exactly in between the two nuclei. It's the negative cloud is more towards this side, partial negative, and this area is partial positive. So the electrons are pulled more towards chlorine rather than hydrogen. Okay, so the shared pair of electron, if you can see here, the shared pair of electron is totally pulled by the chlorine, because chlorine is much more powerful as compared to hydrogen, so it's pulling the electronic pair more to its nucleus. Chlorine is highly electronegative in simple words, so the element which is highly electronegative, which will pull the electronic cloud more, and the element which is low in electronegativity will not pull the electronic cloud that much. That's why a charge difference will be created there. This area will be partial negative and this area will be partial positive. Okay, so such molecule in which you can see an unequal distribution of charge is there, they are called the polar molecules, and the bond is called a polar bond if you face a bond like that. What is a polar bond? A bond which is made between two different atoms, and the bond should be a covalent one. Okay, a bond should be a covalent one, and it should be made between two different atoms. Now you can see here there are two different atoms, hydrogen and chlorine. Okay, these two, they are two different from each other. That's why the bond, the electronic pair is shifted much more towards chlorine in this case as compared to hydrogen. And you can see this chlorine and Cl also. This is a polar bond, H and O polar bond. More powerful one is this one, more powerful one. Nitrogen versus hydrogen. Nitrogen is more electronegative, so polarity is there. Hydrogen versus carbon, so carbon is more attractive. It's having more electronegativity. That's why you can find that it's polar. Now there are two cases. There is a bond polarity, and there is a molecular polarity. Keep this in your mind. Bond polarity is related to this is called discrete molecule, HCl, simple molecular structure. So this simple molecular structure of HCl is having a bond polarity along with it molecular polarity. But there are some complicated molecules where we will study that bond polarity and molecular polarity are totally different. Okay? Are we clear? Shall I move on?
Yes, sir.
Okay.
Yes, sir.
Then the electronegativity difference, which I was trying to explain to you yesterday. In this electronegativity difference, you can see there's a pure 100% ionic character. Sometimes we take that 100% ionic character, and sometimes the 100% covalent character is there. Now, there is 100% covalent character because if the electronegativity difference, I told you a scale yesterday, I'm repeating that once again, 1.7 is 4 and there is 0. You find 100% covalent here, right? 100% ionic here. If you work on this area, this is called polarized ionic. And if you're working on this area, then polar covalent. Okay, in the center this is 50-50 character in the center, so you got 50-50 character, yani it will be 50% covalent, 50% ionic. Are we clear with this part?
Yes, sir.
Keep in mind this scaling is electronegativity difference scaling. When you bring two atoms together, then the electronegativity difference is to be studied and then identified. For example, I'm moving to the table once again, and let us see that table, and we'll pick one molecule, we'll make one molecule out of that table and see what kind of molecule are we getting. I'm trying to work on lithium, on sodium chloride first of all. We thought previously that sodium chloride is 100% ionic. Let us see whether it's really 100% ionic. For 100% ionic, we need to get a net result of 4. Electronegativity result should be 4. Then it means 100% ionic. Let us see, are we getting 4 or not? What is the electronegativity value of sodium? It is 0.9. And the electronegativity of chlorine is 3. So 3 minus 0.9, we got a result which is 2.1. We'll take this 2.1 and we'll see in the electronegativity difference chapter table. Sorry. So the electronegativity difference table 2.1. We are focusing on 2.1. So we got 2.1 to be right here. Now this 2.1 is telling us that the percentage ionic character is 67%. So how much is the percentage ionic character? 67%. So sodium chloride is 67% ionic. This is sodium chloride is 67% ionic. How much it is covalent? 100 minus 67 will give you 33% covalent. Now by 33% covalent, we mean to say that the structure which we were drawing for sodium chloride was, we thought that sodium chloride should look like this, the electron density mapping. Okay, we thought it should look like this. Chloride, bigger one, smaller one is sodium. We thought it should look like this, round, circular, everything. This is for 100%. But now the electron density mapping for sodium chloride is, this is sodium, is a distorted structure. Chlorine is distorted. towards sodium. So this is now 67% ionic.
Sir, can you let Abdul Subhan in?
Okay. It's 67% ionic. Are we clear with this?
Yes, sir.
Any question you can ask now. Let us take another example and see, are we getting some other structure? Let me take lithium chloride.
Sir, can you also add Hamza to the